All right, cool. So we're very happy to have Kim Berghaus here today from Caltech. Prior to Caltech, Kim did her first postdoc at Stony Brook, and she got her PhD from Johns Hopkins under David E. Kaplan. He's important. Kim is an expert on everything Cosmo sort of HEP-pH interfacing, and in particular has done quite a lot of work on warm inflation over the years. So thanks a lot for being here, and take it away. Oh, and I almost forgot to mention the most important part. She has a grant to start a group in Germany, so she'll be moving on to brighter futures.
KIT.
Yeah, sorry.
KIT.
Powerful.
Yeah,
I can't say.
Okay, Robert, thanks so much for the introduction, and thanks so much for having me here. I'm very excited to tell you about this work, which was just this week. I got the news that it was accepted by chiral. So what I want to tell you about, it's all in the title. I want to tell you about warm inflation with the standard model. So what do I mean by that? Oh, click. Oh, no, it works. Okay, so since this is a particle seminar, the standard model is maybe one of our favorite theories. So a big quick reminder, we have our standard model particles, and the force that I want to focus on in this talk is the strong force. So in particular, what I want to tell you about today is I want to combine the ideas of the strong force with what happened in the very earliest moments of our universe during cosmic inflation. And in particular, I want to write down a Lagrangian that gives rise to dissipative effects that lead to particle production that make the earliest period warm. And I want to do it via this interaction. So via an axion-like coupling of here, this is the inflaton field, coupling to the standard model QCD GG dual term. And here, this alpha, this is the strong coupling constant of our standard model. So now this was my spoiler. I've told you everything already. We can go home. No, of course, I'm just...
Excuse me, so it's coupled to the dual, it's more like axion, right? What's the difference?
Very, very good, and we'll go into this. So here my inflaton in a way takes the role of an axion.
Okay.
And in fact, if and I'll get to that especially towards the end of the talk, this F here, the scale, which determines the strength of that coupling, that is something that we're probing in axion experiments. So in a way, this theory, and I'll tell you in details about the theory, we can connect it to experiments and probes that we have today. Okay, so that was very brief. Okay, so let's back up. So the structure of my talk, what I want to tell you about, I know many of you already work on inflation, so maybe the first moment will be a little bit boring, but for those who don't think about it every day, I want to briefly recap what we're thinking about inflation. And in particular, I want to make that recap to contrast it to the scenario of warm inflation, which you may have thought less about in the past. And at first, I'll start at a quite phenomenological level, just talking about roughly the macroscopic phenomena that we can expect from warm inflation. But then, since we're particle physicists, I want to dive into what about the microphysics, what about the Lagrangians that give rise to this dynamic. And historically, there have been some challenges to doing this, so I will go into those. And from then, I will segue into how one can have warm inflation with the standard model by coupling to the strong force with exactly the coupling that I showed you just a second ago. And as we've already had a preview in the question, there will be some implications for dark matter and strong CP, and I'll talk about those as well. Okay, so why inflation? Our universe is incredibly homogeneous and isotropic, but even though different patches across the sky shouldn't have been in causal contact, unless there was a period of a rapid accelerated expansion in the very early universe. If there was such a period, it could explain why different patches that shouldn't have been in that causal contact could have been in causal contact. So they could have all started from the same initial state, which would explain why everything is so homogeneous, and the temperature fluctuations are of the order of microkelvin between the hot and the cold patches in the cosmic microwave background. And in particular, if we ask how large are those fluctuations, so the 2-point function of the temperature, the fractional, the amplitude of the power spectrum is of the order of 10 to the -9. So that's very, very small, and inflation does a beautiful job being able to explain this. Now, we not only have the amplitude of our fluctuations, we also have this quantity of how it evolves over scales that we can measure in the cosmic microwave background. That is the so-called spectral tilt here. And if it was exactly 1, then it would have the same amplitude over all scales. And if it's smaller than 1, there's a small dependency on the scale. And what I'm showing here is a plot of the spectral tilt as a function of this ratio R, which parameterizes the ratio of the tensor fluctuations to the scalar fluctuations. And this is something that over the years we've been very tightly constraining. And one, in my opinion, of the interesting open questions in inflation is many theories, and in particular, maybe the very simplest theories. So let's say we assume something very simple, like an inflaton field with a very simple potential. Those theories would predict a larger amount of gravitational waves, which we have so far not yet seen. So right now there's a lack of inflationary gravitational waves, and trying to detect them would be extremely exciting, but these constraints are tightening. And by tightening, they're ruling out the simplest models that we have. Now let's talk about the simplest models. So I just said inflation is a period of accelerated expansion. Now, how can we achieve such a period? General relativity tells us that the content of our universe dictates how we're expanding. So to have such a period, we need an energy density with maybe a little bit exotic properties, where the pressure over the energy density is smaller than about a -1/3. Now, we can achieve this if our universe was dominated by a scalar field. And in particular, if the energy density is comprised of that scalar field, and that scalar field is very slowly rolling. So we're dominated by the potential energy of that scalar field over the kinetic energy. Now, how can we be in this parameter space where we're very slowly rolling? We need some type of damping. And in the canonical picture, that damping is just given by the expansion of the universe itself. So because our universe is expanding, we automatically get this Hubble friction term, which can allow us to be in the slow roll and have these properties that we desire. And being in slow roll is what allows us then to explain the observations that we see in the cosmic microwave background, and we can recast it as a requirement of on the properties of the potential, and define a slow roll parameter that has to be very small. So this is the standard picture. You probably knew all of this already. What I want to emphasize here is we really have only one thing here in this theory. We only have the scalar field. And now the fluctuations of that scalar field is what gives rise to the amplitude of the power spectrum. And we only really have this one quantity here in our setup. So because we only have this one quantity, we also only have one scale. We have the expansion rate of the universe itself, that's Hubble. So that's our scale. And this gives rise to the quantum fluctuations that seed our universe. And similar, because we only have that one scale, if we ask, what about gravitational waves that are seeded? They're seeded by the same source. It's also Hubble that seeds them. And because of that, we have a relationship in the tensor to scalar ratio that is, because we only have this one scale, which is given by Hubble, so that relationship is quite fixed. And it is this prediction that then over-predicts the amount of gravitational waves that we would have expected for the very simplest models, like taking, for example, a linear potential like the one in the sketch, or something quadratic, which you may expect as your simplest possible choice. And that now puts us back into this image where our constraints lie down here, but a simple potential would be up here and already rolled out. So where does it leave us? Of course, inflation is still our most successful theory of explaining the early universe. And we have many, many candidates that do a great job being able to reproduce this data. The one thing that is true about all of them is that we need additional complexity. We need additional ingredients to be able to conform with the data. So that in itself is not an issue. I just want to emphasize it. So now what I want to do and what I want to tell you about is I want to take this additional complexity and I want to put it into something that we may expect is already there. So particles like to interact with other particles, and us especially, we like Lagrangians. So what I want to ask is, let's consider particle interactions. So instead of just having our inflaton there, let's consider coupling it to some other stuff. So if we do that, we can be in a slightly different picture. We can be in a picture where we're not only in a universe filled with only that scalar field, we can be in a universe where we're also surrounded already by a hot bath of particles that maintain a temperature. And my definition that I'm using here for inflation to be warm is that that temperature, that scale, has to be larger than Hubble. Then we have a sense in which we can say that our system is thermalized, and a sense in which we have thermal fluctuations in our system. Now, what changes is that if we ask how is our inflaton field evolving, is we no longer only have Hubble friction, which slows down our field. We can also have this thermal friction coefficient, which is what is extracting the energy from the inflaton field and is dumping this into this radiation sector. So now we have two equations that tell us about the dynamic of our system and how it's evolving.
Does this mean that, excuse me, that the temperature is always bigger than 10 to the 13 in this model? Because Hubble is 10 to the 13 in cold inflation, and you're going to use the same.
Well, in warm inflation, because now we have a different, so why is Hubble that? Because you can relate it to the CMB observations, but now we have a different scale in the problem.
CMB at a lower H.
Yes, generically you lower H because you can raise T. So conceptually, let's take a look at the equations. So this is just your regular continuity equation of how radiation evolves in the universe, but we have a source term here on the right-hand side. So we have a sink term, which is Hubble. It's just telling us that if we have a radiation, our universe is expanding, it's diluting. Without the source term, we would get a regular redshifting as a to the negative fourth. But now we have a source term here. And in particular, the key idea in warm inflation is, and also the key challenge, is that you want to have a source term that is large enough such that you can maintain this balance where you can source particles at the same rate at which you're diluting. And if you do that, then your temperature, which is related to your energy density, roughly remains constant. So you're having an equilibrium temperature while you're in this expanding universe. So now what changes here is now the fluctuations of the inflaton field, which seed our large-scale structure, no longer only has Hubble as a scale that is dictating how it's evolving. We now also have a temperature as a new scale. And this is a very interesting point to me. Conceptually, it's in that picture, it's classical fluctuations that seed everything rather than quantum fluctuations. And now what follows from this is because we, in a sense, decoupled what gives rise to the gravitational waves and what gives rise to the scalar power spectrum, is we're able to drastically suppress the tensor to scalar ratio, because this gets an enhancement from that temperature that's larger than Hubble, but the gravitational waves, unless we're approaching temperatures of the order of M Planck, they're not thermally produced, so they're still dominantly produced by Hubble. And then the other thing that I want to point out here is that we have an additional source of friction, and that now makes it easier to fulfill the slow roll condition. So previously, our potential, in a sense, have to be very, very flat because Hubble is very weak. But if you have additional particle production, in a way, you can have a steeper potential and higher friction, and you can still be in slow roll.
How firm is this functional form of the fluctuation?
This is very conceptual. I mean, you can, depending on what your friction looks like, you also have dependencies on the ratio of friction over Hubble.
Okay.
Yeah, this is more conceptual.
Yeah, just it can depend on that.
Well, it always does depend on the temperature, but it can be more complicated than that.
And what keeps temperature at a constant value?
It is basically this friction coefficient, and really, I just wrote it here very phenomenologically, and this is the crux of the entire issue, and this is what I'll dive into now, because I just said particle interactions, now look at this friction. But the really important thing is, can we write down a Lagrangian where we get this behavior? This has been a long question that people have been asking for 30 years, and I'll explain how we can get that. Yeah, and let me maybe say, this idea of warm inflation was proposed about 30 years ago by Arjun Barrera. So this idea has been around for a long time.
What was the motivation? What problem were they trying to solve at the time?
You know, I think, so I wasn't around then. So I didn't follow, I think, naturally the progression, but from my understanding, it was more of a question of what could inflation have looked like? And in a way, this is an alternative picture to the one that has, I think, become more the canonical version. And this one seems more like a more exotic alternative. Or today it's treated as a more exotic alternative. Maybe if I do a good job, I can convince you that maybe it's quite a viable alternative.
Is the expansion still going to be exponential?
Of the universe.
Yeah.
Yes. So in terms of the hierarchy, if you ask, the energy density of the inflaton still dominates. So you're still dominated by the potential, and then your energy density in your radiation dominates over your kinetic energy, but it's still subdominant to your potential.
So I guess if there's Planck scale that's sort of doing this like seesaw, because you have temperature bigger than h, where h is given by well, h squared is given by v, or h squared and Planck squared.
It's exactly what you said with the M Planck. The energy density, yeah, the potential is still,
because it's h time. Well, the scale there is h m Planck, or the square root of h m Planck, right? Because h is still dominated by v. You're saying
exactly, that's why I'm saying, and because of the M Plancks in there, you can have that both hierarchies be true at the same time. So if one writes down like both of these hierarchies, one can show that there's a large regime where you can fulfill both.
Your statement that the radiation is larger than the kinetic energy, that's only true in strong warm inflation?
That's right. That's
Yeah,
right.
okay.
Yeah. So one can distinguish between this being larger than Hubble and smaller than Hubble. People call that strong and weak. So so basically, if or not. Oh yeah. So in this regime, you would have V is much larger than rho is larger than and then in the other regime, which is the weak regime, it would look like that. Yeah, thanks for pointing that out.
I guess the point is that you're also not going to need as flat a potential as cold inflation. Is that true? You're still going to require flat potential.
Well, it depends a little bit on how exactly you define flat. In terms of your Transplanckian field excursions, you can, or in terms of your field excursion, you can reduce delta phi that you have to travel. So if in cold inflation you need, in a single field model, you need 20 M Planck, you can go down to like order 1 M Planck because you have that additional.
But you're still going to need you're still going to have a flat potential, relatively flat.
Yeah, if one ends up comparing with observables, and you find that you still end up needing to be quite flat. And I'll show couplings in the end, and that will show that your couplings need to be quite small, which translates your potential couplings, which translates to you being flat.
Maybe I'm jumping ahead though. So if the universe is expanding exponentially, rho of the radiation would like to go down exponentially, but you're pumping more energy into it continuously. And that's got to come from the potential.
That's right. So you're exactly striking this balance where you're diluting at the same rate as you're sourcing, and that source term extracts the energy from the potential. So one thing that I didn't emphasize, that in the strong regime of warm inflation, you can maintain a period of 60 or so e-folds or longer, and then at the end of inflation, you can smoothly transition. This rolls down, your radiation stays roughly constant. You can smoothly transition into an FLRW universe without any additional reheating. It's just very smoothly, this goes to the bottom, now the temperature stays. And when it stops being sourced, then it starts redshifting like regular radiation.
But doesn't that tell you that V is changing so that you're not in the region where you're exponentially expanding? If I'm continuously taking out energy of V, then V can't be constant, right?
I mean, really, the energy is coming from the kinetic energy, not from the potential energy V. And so in that sense, that's actually kind of what's keeping you slow though, is you're getting rid of the kinetic energy.
Okay. And if there's no kinetic energy to start with?
Well,
I guess you like strike this balance where.
Yeah, so in a way, this is an attractor solution. So let's say you start out, and of course you need to have a potential. If you're just sitting there and nothing happens. But if let's say you sit here and you start out with zero kinetic energy, you start rolling. So you build up that.
You're going to show us the potential.
Yeah. But yeah, so this is an attractor. So you'll build up to maintaining that steady state temperature. And I think the point that you made here, there's an analogy in cold inflation. You can be in slow roll on one in the beginning, and eventually you start oscillating, and that's when you reheat. And the same is happening here. You can have a long period of slow roll, and eventually you transition out of that regime. Okay, so let's get to the crux of the issue, because we just wrote down this friction coefficient and we said everything works out beautifully, but does it actually? And this has been a big question for a long time. So what we need to do is we need to write down a Lagrangian so that we know what our interaction is. And here I've kept the interaction very general for now. I just coupled it to a current, which now here has my interacting particles. So now if we ask how does that affect the equation of motion of the inflaton, we're linear here in phi, so we know that we should be linear in this interaction term in the equation of motion. And in particular, what I've wrote down here is the expectation value of that current interaction, because we're in a thermal system. So there's a thermal expectation value of what that current is. So let's say if that was two scalar fields, then that would be at the expectation value of those fields. So now we can try to calculate this, and this is our thermal expectation value. So we can use techniques in thermal field theory to ask what this quantity is. And specifically, to do this analytically, we need to make some assumptions. And one assumption that we can make here is that we're in a regime of linear response theory. What I mean by that is our phi is evolving slowly compared to the scale of the interactions in the thermal bath. So our particles are interacting very rapidly with one another. They're what maintaining at finite temperature, and phi dot is evolving very slowly in comparison. And now we can ask, what is this quantity? And I've here already very suggestively written it as a thermal mass term, linear in phi, plus this friction coefficient. In a full calculation, these coefficients are not ad hoc. You can fully calculate them from thermal correlators in your theory once you specify what your interaction current is. But the big point here, and this is maybe not surprising, is if we're in a thermal bath, we get a correction to the mass of our particle, and it's the thermal mass of the particle. So if this were scalar fields, then this thermal mass would scale as the coupling squared times the temperature squared, and gives us contribution here. And as you can see in this expansion, this is the leading order term. This is a sub-leading order term. And what was a big issue for a long time, and why for a long time people thought inflation can't work, there was even a paper written that said, is warm inflation impossible? I think that was the title. Is exactly this point that you seem to inadvertently be getting this mass correction. And that, of course, now enters your potential because you have an additional contribution to the mass. And there was an argument that if this mass term is larger than this, which is generically what you seem to be getting, then you can not be in an inflating universe where you get a friction coefficient that keeps you warm during inflation. So it's this question, can we do this? Is this two sides of the same coin where if we want this one effect, we also always get this other effect? And some early models were proposed and they used a lot of ingredients and they weren't very simple that tried to achieve this hierarchy. One approach was very heavy mediator fields, for example, and you needed order 1,000 particles to get a sizable effect here. So that maybe you don't want to replace your canonical simple inflation with that. So something that I've worked on in my PhD extensively is the realization that if we make this coupling a pseudo-scalar coupling, and here I'm considering now not yet QCD, we'll get to QCD in a moment, let's consider just a pure Yang-Mills. And let's couple the inflaton field to a GG dual term. And we're at finite temperature here, so I'm assuming we're at a temperature above the confinement scale of set group. So what makes up the radiation are basically the gauge bosons of that group. So now we have this expectation value here, and due to the symmetry of the system, this thermal mass correction is very much suppressed. So another way of saying it is if we have an axion is a pseudo-Goldstone boson, it gets a correction to its mass, it stays light. So for this type of coupling, we get this very interesting hierarchy where this term here is very, very small. But if we ask, what about the particle production here? What about this dissipation? We actually have another effect here where we get an IR enhancement for the production of particles. And in particular, we're enhanced by so-called sphalerons. And I'll talk in detail now what exactly happens here. But what I want to emphasize here is that in a way, you kind of get this perfect storm where your symmetry forbids this term, but then this one you want to be large. And we needed it to be large for us to be able to maintain this finite temperature. And we get an enhancement by something that is not an ingredient necessarily in very many theories. So sphalerons are inherent to a non-trivial topology of our theory. And they're doing here exactly playing the role of helping us produce a lot of particles. And I'll talk now about how they do that.
Excuse me, what this epsilon field, what it is in nature? The field which is coupled to inflaton.
It's the GG dual, so it's the gauge bosons in here.
Okay,
And how you calculate this is from the Minkowskian correlator of this interaction.
yeah, this I understand. But you understand that sphalerons only become effective in the confining phase. Above, when the temperature is higher than the confining phase, it's
Okay, yeah, very, very good. And we'll dive into exactly that. What you're saying is that the barriers at the large temperature become low, and that's exactly the effect that we're exploiting here.
I see.
That's exactly actually what we're using. So it's that what we're.
That looks just like a decay rate.
Yes. So why do I say that we're dominated by our physics? So if we were in the regime where our inflaton was rapidly oscillating, then we would get a perturbative contribution to this, and then it would be closer to the decay rate that we're more used to calculating. But this response,
That interaction. Well, I guess is there a mass to phi? What is the mass of the inflaton?
that's given by the potential.
Okay.
But this is a frequency. In a way, this coefficient here depends on the frequency of phi.
Well, if I mean, I have the linear term there, it looks like I have a decay channel of phi to two gluons or whatever your gauge bosons are.
No?
But we're not having particles on shell that are decaying. We're having this background phi field, and we're in a way classically extracting this energy from that field into sort. It's closer here to a transport coefficient than to decay rate in this context.
I think the same.
Okay, so maybe I'll go ahead and I'll explain a little bit how this comes about, because I know I just threw all of that at you, and I'm not expecting you to bite. I'm gonna tell you about how we get here. So before I dive into the physics, I want to briefly talk about sphalerons. So I gave this talk at Cambridge actually, and I was lucky enough to run into Nicholas Manton, who discovered the sphalerons together with Franz Klinkhammer in 1984. And he showed me the original correspondence that they got from the journal back then. And I'll highlight here the part that I thought was the most relevant. So I'll give you a second to read it. I thought it was very interesting. Apparently there was some pushback to calling it sphaleron. Yeah, so Nicholas was very happy that they succeeded in naming it as Sphalerons. And I was very happy to have the chance to meet him, who discovered this crucial ingredient. And yeah, Sphalerons are very interesting theoretical objects. And I kept this here. So here I asked Claude what a Sphaleron is. Claude is the brother of ChatGPT, basically. And I kept this in here because Nicholas Manton said that he loved the way that Claude described his discovery. So I thought I'd share it with you. So for those of you who have not thought much about sphalerons before, in a way, it is really, it is a feature of non-trivial topology in our theory. So if we have a U1 theory, for example, which is topologically trivial, we don't get sphalerons. But if we have an SUN theory, we do get them. And it is the statement that we have different vacuum states in our theory that are connected by a winding number. And you cannot continuously have a gauge transformation from one to the other. You need to have a large gauge transformation. In a way, you have these barriers here, these energy barriers to go from one to the other. And usually we talk about instanton effects. That means we're tunneling from one to the other. But sphalerons are particularly unstable solutions, the classical solutions when you go atop of this barrier. So in terms of what you could think about is, rather than tunneling, if we want to go from here to here, this is a non-trivial IR configuration of our gauge fields. So to go from one to the other, our system needs to basically go on shell with this configuration before it can go into the other vacuum state. And the length scale at which these sphalerons form are 1 over alpha t, and then the decay scale is alpha squared t. And from we can define something which is called the Sphaleron rate, which has been of great interest in various different contexts. But what this quantity basically is you could ask, if you have finite topology, how fast does it diffuse? And the Sphaleron rate tells you how fast you're diffusing. It's a diffusion coefficient. And due to roughly this the scaling argument, the scaling of that diffusion of topological number is given by n to the fifth, with n is the color of our SUN. And then alpha is alpha to the fifth to t to the fourth. And that comes about from roughly these arguments. So now, why am I telling you all about the diffusion coefficient? We can, if we ask about diffusion and friction, those quantities are very intimately connected by the so-called fluctuation dissipation theorem. And if we know what the diffusion is in our system, we can use it to derive what the friction is in the system. In the limit in which the frequency is very low, which in our case, because we're slowly rolling, phi dot is very small, so we can use this diffusion coefficient to derive what our friction is. Okay, so let's look at this in a slightly different picture. So we have this potential here, and as was already brought up, this is the zero temperature picture. At high temperature, these barriers actually become much, much smaller. That's the same statement as saying that Actually, no, I don't want to. So these become much lower. And the reason for that is because if we are at a finite temperature, it becomes much easier to overcome these barriers. At some point, it's trivial to go from one barrier to the other because we have enough energy in the system. So this cartoon here is exaggerated. These wiggles are really tiny. What really happens here is that there are almost no wiggles anymore at the temperature above the confinement scale. But what happens here is if we integrate this by part very roughly, we can write this as phi dot over f times this Chern-Simons number. And this inflaton field rolling gives a linear potential to our vacuum topology number. And it forces basically transitions between different vacuum numbers. And between each transition, we go through a Falaron configuration. So in real time, we're sourcing these finite energy IR configurations, and we're forcing them in one direction. So we keep transitioning, and it is these IR configurations of the Falarons that enhance the particle production, because we're giving this bias to transition, and every time a Falaron decays, it decays into gluons, and that gives us our particles here. And exactly from the diffusion rate, we can ask what is the friction coefficient. And we can again here recognize our alpha to the fifth, and then t cubed over f squared as the characteristic particle production rate that we would expect from this coupling. And this is applicable in the slow roll regime. If one were to consider a regime where phi rapidly oscillates, there are other processes that also contribute, particularly perturbative processes. But in this regime, in this IR regime, we're dominated by IR contributions, which are given by these Falarons. So now this friction that I wrote down in my equations for warm inflation earlier, where does it come from? It comes exactly from this coupling.
Excuse me, I don't quite understand how do you get all these scales. In QCD per se, ignore the quark masses for the time being. The only dimensionful parameter is lambda QCD, right? So the height, I mean, the Falaron, the peak of the Falaron, if you want to find the energy of the peak of the Falaron, and this poorly defined in the infrared theory, okay, lambda QCD will enter, but then at weakly coupled, it will be enhanced by 1 over alpha S, right? In the at weak coupling, like in the Higgs regime. The energy of this Falaron is MW divided by alpha SU2, alpha of the standard model.
Well, you're thinking about electroweak Falarons right now with MW.
No, I can think that's a question to QCD Falarons, but qualitatively to define how high you wrote that T has to be larger than E Falaron, right? In the previous
Yes.
slide.
Okay.
But what is E Falaron in the theory like QCD, nobody knows. Quantitatively.
So we are very far above the confinement scale of our theory.
Yeah.
So there is no delicate balance of overcoming this Falaron barrier. It's very trivial to go from one vacuum to the other. So this finite barrier here, and this is why I'm saying this is a cartoon, these are really tiny, it doesn't enter here. There's no energy cost to going from one vacuum to the other.
Okay.
What matters more is the rate at which we go from one vacuum.
So you take your temperature T to be much larger than lambda QCD.
Exactly.
Whatever you need, you take. Then, of course, the very issue of Falaron, because you are sitting much higher than the would-be Falaron in temperature. What is a Falaron? It's some fluctuations which is so small at this scale that it's probably irrelevant. And the density of the decay, if you said that easily decays in the Higgs phase, when they know that the gluon acquires a mass MW, it decays on a very large number of W's, and it's possible for Falaron to decay in a very large, but like 1 over alpha W bosons. That's because the Falaron mass is equal to MW divided by alpha, which alpha is supposed to be small. So the mass of this phaleron is much larger than the mass of the elementary excitation, so it can divide, it can decay into huge number of these elementary excitations. But if you are in QCD per se, what is elementary excitation? Raw meson.
No, we are at temperatures way above the confinement scale. So we're predominant, and so far I haven't yet mentioned explicitly QCD. So we're in an SUN,
Yeah.
and what we're decaying into are the gauge bosons. That's all. And like you said, we can estimate what number of gauge bosons would you expect per sphalon configuration, and you get some scaling that goes as 1 over alpha. But there's no issue here with the mass of the sphalon. We're at very high temperatures.
Okay.
And really, this is a cartoon picture to kind of show what is going on, that we are transitioning in our vacuum, and that we are having a bias transition here.
Okay.
But the barriers and that it doesn't affect this. And the argument, this calculation also doesn't rely on this cartoon picture. This is not an estimate. You can derive this using the fluctuation dissipation theorem from the diffusion from the sphaleron rate itself. So this is a very robust result in this regime, and it's well understood by thermal field theory experts that this is the rate that you get in this regime.
But you see, if you are very high energy, very high energy, like T times alpha of T is very large, then the very notion of Chern-Simons number or topological number of which sphaleron is semi-integer, it becomes meaningless because there are no tunneling, okay? So you cannot focus your system to be, let's say the sphaleron topological number is 1/2, or 2 sphaleron it could be, or 3 sphaleron, 3/2.
Yeah, like what you're saying is right. Exactly at these temperatures, it's trivial to go from one configuration to the other.
Yeah.
And that's exactly the point here. The point is that we have a bias. So if we didn't couple to the inflaton, it would be completely flat. We could go in any direction, back and forth fluctuations in any direction. Right? But if we do have this coupling to the inflaton, and the inflaton has a finite speed, we exactly give a bias. So now we're not going in the direction of lower Chern-Simons number. We're going in the direction of larger Chern-Simons number.
But why what you draw here is a decrease in overall, a decrease in function. If temperature is very high, it's very easy to increase, to have many units of the sphaleron mass. And I don't see the reason why it should go down, why it's not flat.
Well, you can just, you can write this as basically, mathematically, you can define your Chern-Simons current, and then you can integrate by parts and keep track of the classical components, so you're neglecting spatial fluctuations. And then you get here the K0 component of your current, which you can identify with Chern-Simons number. And then you can see by integration by parts now the time derivative hit this inflaton field. So if you now just ask like what is here in front of your Chern-Simons, you exactly have this term, which exactly gives you a linear bias.
So, I mean, the first term, this looks like the linear bias, but not the second term, there's no.
The second
Find out.
one, yeah, the expectation value.
You mean this one?
At high temperature.
I think we should ask why
high,
it goes down, but
yeah,
it may be a related question. At least I know in electroweak theory, once you get above a temperature, I don't remember, 10 to the 10 or 10 to the 12 GeV, there's no sphaleron interactions at all.
it's very insignificant, it's very insignificant.
It's only in the range, but.
I would expect that it should be Gigi dual at high temperature, it's still defined, but it's large. It cannot be, on which scale it be, there is only lambda QCD or the mass of the elementary excitation and the temperature. So if the temperature is very high, why Gigi dual behaves like this, I don't understand.
Maybe let me ask a slightly different question, maybe related. Why don't you do the particle production calculation, compare the result in vacuum and with Bose enhancement, what would be the scaling of this frequent term?
So I,
From
yeah, so,
enhanced rate, this calculate.
yeah, I could show you that result. Oh. Or I could have shown you that.
Where are you going to invoke the language of scalar? So I'm just doing particle production.
Yeah, so if you ask basically, what is this rate in all generalities across all scales of the inflaton in terms of particle production rate? This is a frequency dependent quantity where the frequency is the frequency of the inflaton itself. So because in slow roll, we're in the very much IR regime. So we're taking the limit of omega going to 0. But of course, that is only that specific regime. You could ask for any general motion of the inflaton field, taking all processes into account, roughly what does your rate look like? And you find that there are indeed components that can be larger, particularly when you have a larger inflaton frequency. And talking about the Bose enhancement and your particle production, that term exactly enters here. So this is the statement that if you're going into a classical reheating regime where your inflaton is rapidly oscillating, you do get perturbative particle production, and that is large. And in that regime, it's larger than what you get from the spalarons. However, in the limit that frequency goes to 0, these terms become all small, and instead you're dominated by the IR process.
Let me interpret this expression. The right-hand side is the Bose enhancement, the second term, right? The first term you said is the spiraron enhanced rate.
Yeah.
But in which coefficient the spiraron enhancement came in the first term? So if I just do a particle production, right, which is the kinetic energy of phi converts into a pair of gluons. I can do it.
Yeah.
What would be the scaling there?
It would the leading order term would also be alpha to the fifth t cubed. So you get the same scaling actually. You get alpha to the fifth t cubed over f squared, but you get a phase suppression that is larger. So if you do compare them side by side, you find that the
just 1 over 8 pi. That's it.
Yeah.
So you want to the factor of 8 pi matters a lot for you.
What factor of 8 pi?
Is that there's a phase suppression.
From the perturbative, I mean, at the end of the day, it comes down. You can calculate the perturbative contribution and the non-perturbative contribution, and the non-perturbative one happens to be larger in this regime. That's.
Yeah. So can you clarify what do you mean by IR? You mean IR here means when the phi dot is comparable to the scale where the new theory confines. So the spiraron is more active configuration.
No, with IR, I mean the limit in which the frequency of the inflaton goes to 0. That's what I mean with IR.
Which means phi dot is small.
Yeah.
So you want phi dot. So that's the amount of energy you have to inject into this new particle. That's where is the friction, right?
Right.
So when phi dot is small, that means my available energy is small, right? So small compared to what? I think it's the order one compared to the confinement scale of that sector. That's where that's the only regime spiraron rate can kicks in and dominate the calculation. I assume that's what you.
But the confinement scale doesn't enter here.
Well, when you say something small, it has to be compared with something. Okay.
Yeah, you're right. Okay, it's compared.
With another energy scale, which is a confinement scale. Otherwise, I cannot see, as Misha said, why spiraron comes with.
There are only 2 scales in the problem. Forget about heavy quarks, 2 scales, lambda QCD and temperature.
Right.
So temperature is much larger than lambda QCD. That's understandable.
Yeah.
With spheron at large temperature, in fact, spheron has a very, well, at least qualitatively, we understand that it is from, as Keith mentioned, from the standard model. It's just a coherent state, very coherent state of 1 over alpha W's, where alpha is calculated at the scale of the spheron mass. So alpha is pretty small, because spheron mass has this enhancement, right? Smaller energy. So if you now say that your temperature is high, there are no W's, right? It's just gluons. okay, at very high temperature, which means that they fly around in the medium like crazy. When they fly, I mean, next to each other, they don't have time to become coherent with each other. So the spheron, even if it has some effect, it only comes from the very infrared of this picture. So so forget about in the first approximation, I would say forget about spherons. You are in the regime of quark-gluon plasma, very heated plasma.
No quartz.
Huh?
No quartz.
Yeah, gluon plasma, extremely heated. So, and work from it. It's my opinion, but I'm sorry, I don't want you to drag into this direction too much.
Well, maybe I could say two things. One scale that is relevant is what is the momentum of the particles that we're producing. That's the other scale that enters. And we can perturbatively do the thermal field calculations when we have large momentum. But at low momentum, eventually when we get of the order of alpha t, we can get strong effects here. I think that's the statement that we have these IR configurations that can become like.
Can I check, is alpha T a word allowed to QCD, or is alpha T much bigger than QCD? That's of course important, depending on how higher temperature. Are you in the hard thermal loop limit or what?
No.
Then alpha, so wait, so the temperature is not that high? If alpha T can be a scale that's comparable to lambda QCD, the temperature is not that high.
Yeah,
Temperature is
no.
very high, alpha T is still.
So temperatures are typically, yeah, no, we're way above the confinement scale. Yeah.
Then alpha T is still a huge. Maybe I misunderstood.
Yeah. Yes. That's why I'm saying we're not at all close to the confinement scale. That's why it's easy to produce these particles. And then I want to say, oh, okay, I guess I'm going back here. One thing that I want to say. So I tried to give you a feeling for what's going on. At the end of the day, what we're calculating this coefficient from this interaction. This is a very well-defined calculation. This is a Minkowskian correlator in thermal field theory. So what we're calculating is the Minkowskian like 2-point function of this interaction here. And we can just ask what is it? And we get a result for what this coefficient is. So we can understand it in terms of these pictures, but at the end of the day, by writing down this Lagrangian, we fix everything about what this quantity is, and it has been calculated to be this, right?
Maybe I can add something.
Sure, go ahead.
Hopefully we'll clarify and not make things more confusing, but Misha mentioned that there's lambda QCD and there's the temperature, but there's also another ingredient here, which is the fact that the scalar is rolling. So you see this phi dot over F times N, that phi dot over F is acting as a chemical potential. It's like mu N. And so the fact that the scalar is rolling, that's what causes the tilt of this potential. If there were no rolling scalar, it were just some finite temperature, then you would have the little tiny wiggles, where the higher the temperature, the smaller the wiggles. But the fact that you also add in this phi dot over F, that's what causes it to tilt.
No, but I'm talking about the coefficient in front of phi dot. Phi dot, it's presumption that we have this phi dot, right? I don't have anything against this phi dot. I'm talking how do you calculate at very high temperature, what is the coefficient? Like with the Hubble term, you know the Hubble from experiment, right? If you didn't know Hubble from experiment, you would not know even the constant, almost constant term. Now the question, what is your epsilon? And I am trying to argue that epsilon, at least, maybe it's my ignorance, I don't quite understand how it appears and what it really means. At very high temperatures, what I know for certain, we have a heat buff of gluons which fly in all directions like crazy because the temperature, right? Temperature is very high. They are not bound. And if they are not bound, it's like ideal gas of gluons, which are in the heat bath, and the heat of the bath, the more, kinetic energy they have. Right? If there is a little bit of infrared interaction there, okay, it changes a little bit, but it cannot dramatically change the.
My understanding is if there were no scalar with just the bath, then the bath doesn't care what term Simon's number it sits in, they're all the same. If you have a rolling scalar, then it makes it want to go to, in this case, higher number. And so as it goes to higher number, then it's
driving.
energy, and
Yeah.
where is that energy coming from? It's coming from the scalar.
Yeah.
So in that sense, it's slowing the scalar down by sucking energy out.
Okay, what is the slope if you average this on your picture? Average about the small oscillation. What is the slope? The coupling F, which is in your picture, what it is?
That F,
Yes.
that is the coupling to, that's the coupling strength here.
So you say it's not related to temperature. F is some big number, but it's not
Well, that's just-
unrelated. to-
Yeah, it's the strength of the interaction, because this in a way tells you the rate at which you're driving these transitions.
What would I get if I just did a perturbative calculation using that first term?
That's what the result that I showed you.
So, but if I calculate it like this was a decay, right? Because, I mean, it appears in that equation like a decay. If I had a decay for phi, it would appear exactly like that in that equation. And this is a linear term in phi, and so I can calculate a rate of phi going to 2 gluons.
The first non
So there'll be a 1 over f squared, so you've got that. There will be,
a t cube, you got
well, I
that.
don't know that there's a t, well, I don't see necessarily the t cube right away.
Well, dimensionally, if you have the 1 over f squared, then you need to have the t cube.
Well, yeah, maybe that's the only other scale that can come in. And then, okay, I would naively say alpha squared, so I don't, you got
I
it.
would say naively T4, right? Because dual has dimension of 4. But,
Right, but you have some vertex with some d mu's in it, so you're
Yeah.
gonna get some d mu's and.
but then you have alpha to the 5th, so it's the 5 loop calculation, which I don't quite understand, interpretively, why it should be, what's the result in 1 loop? How come?
Well, alpha squared would be tree level, right?
No, but alpha gamma is proportional to alpha to the 5th, of course, NC, we can rewrite it in terms of the 4th coupling, so it's natural, it's a planar graph. But alpha to the 5th, each loop is alpha normally. Or if it has more legs, it may be like 10 gluon legs, but it's not what dual naively is just 2 gluon legs.
Right, that's what I say, the perturbative. GG dual, and then your vertex would have some d mu's in it, right, or some p mu's in it.
But alpha doesn't have anything to do with.
No, that's what I'm saying. I would expect alpha squared if I was just trying to calculate it. So I would get alpha squared over f squared. And I guess the only other dimension in the problem would be t cubed. So I can understand where that would come from. But that's different sort of picture than what you're arguing, because I don't even mention scalarons. I'm just saying I have that interaction. And I get a dissipation rate of phi going to 2 gluons.
So these rates have all been calculated, and I don't have the reason right now ready, but the leading order contribution, the alpha squared term vanishes perturbatively. So your leading order perturbative contribution also scales at alpha to the 5th.
Could be that there's a p mu squared that's 0, and then you have to go to the next order. That's possible.
So not an alpha.
Well, it could be that the alpha squared computation gives 0. Without doing the calculation, I wouldn't know, but I could believe it.
Yeah, that can do, but with alpha at the level of alpha cube, what is that?
I don't know.
Can I just check, is it actually important that we call this scalar friction?
That's right.
Gluon friction, I think that's what you're asking.
That's what I'm
If we
saying.
could short circuit a lot of this and just call it gluon friction, And then questions that I've been resisting asking also wouldn't come up, and many questions people have been asking wouldn't come up, and then all would be fine. Is it really important that it's scalarized?
No, actually.
Just gluons and anyways,
It's not that important. What is important though are that we're getting these vacuum transitions, and that's maybe if I'll get to it, I can try to make that point, and we can maybe go back to this discussion in a little bit, because the question is, so far we were in the SUN picture, so now the question is, what happens when we want to do this with QCD? And here it starts mattering basically what happens to our vacuum structure, because this phi dot over F term gives us the chemical potential for Chern-Simons number, but we know this very well when we have fermions in our system and we go to a different Chern-Simons vacuum, it has an impact on those fermions, and that impact actually very intimately interplays with the mechanism here. So in particular, if we have these fermions, we have an axial charge, an axial current, and then an axial charge that we're building up as we're transitioning. So you could think that with each transition, we're putting more left-handed compared to right-handed fermions or quarks in our system, and it can build up a countercharge to the chemical potential built up by the inflaton itself. And then the question is, are we back in this picture where we have no preferred direction, no driving term, and does the friction shut off? And this is what was suspected. And one of the big results, and I'm happy that I'm actually getting to tell you about them, is that this actually does not quite happen. Even if we have quarks, and even if we do build up a chemical potential, we have Hubble dilution in our system. So what does that mean? It means all this counterweight that we're building up, it is continuously diluting. So it's continuously shrinking. So we do get a counterweight, but it doesn't exactly balance out the chemical potential that we have. One can see this in terms of the differential equations. You can write them down for your inflaton, and then the chemical potential itself, the axial chemical potential of our quarks, is also evolving in time. And you can, and very crucially here, Hubble cannot be neglected. It is an important effect. So even if Hubble here is small, here, the fact that it's not conserved really matters, because we are continuously decreasing this counterweight, which means that at the end of the day, we get an effective friction coefficient, which is what we would have naively expected from what we have in the SUN. And then we get a correction term that takes into account the evolution of our chemical potential, the chiral chemical potential, where here this 3H functions as a chirality or axial charge violation, which in this case is just the expansion of the universe itself. You could imagine, of course, in the standard model, we also have other sources of axial charge violation. We have Yukawa couplings. They are subdominant here. Hubble is a larger effect. But you could consider another theory where you have fermions, where scatterings itself could dominate the relaxation mechanism here. So now where does that lead us? That means we have a regime where this term can be small, in which case nothing has changed. We have our regular scaling with temperature. But we can also have a regime in which this term does dominate at the end of the day. And then we get a different scaling. We get a scaling that goes as temperature squared. And it is actually quite important what the temperature dependence is in our theory, because all the observations that we calculate in inflation, they intimately depend on what our temperature dependence is. So very generically, with basically QCD, we get all of these regimes, and we can transition from one into the other. So for the results that I'm going to show you now, I'm going to remain in the regime where this correction term is small. And that's just because practically not all observations have been calculated for when you go outside of that regime. But when you're in this regime, we know exactly what our observations look like. And now here's a comparison. So this is the plot that I showed in the beginning, where for the simple potentials, it was difficult to be down here. Warm inflation, as we discussed, very generically suppresses the tensor to scalar ratio. That suppression gets larger the bigger the friction is compared to Hubble. And here I'm showing what would happen when we have this interaction term plus an extra potential for the inflaton. That's just our regular inflaton potential. And here phi to the fourth is able to basically reproduce the spectral tilt that we observe in the cosmic microwave background. And now in the setup, there's only one free parameter left once we're considering CMB observations. And that parameter takes you basically from the strong regime of warm inflation down here to the cool regime of warm inflation. And we can see that across basically this parameterization, all of them are very easily able to explain the observations that we have without there being many free degrees of freedom at all. Like this, we have basically just this line that is our prediction. So what are the ingredients here? The ingredients are, we have an inflaton potential. Here we have a phi to the fourth one. So we have this free parameter lambda. And the other free parameter in the theory, in the sense this f, that becomes fixed once we take into consideration the scale of our CMB. So all we did is we took our inflaton and we turned on a coupling to standard model GG-dual. And then we considered a UV potential. Yeah, so
not also moving to my scalar field, but how could you apply it?
Yeah, so so this is a great question. Usually for axions, we like the potential to come from the GG-dual term itself. Here that's not possible because we need to be at a temperature much larger than the confining scale. So we don't get this non-perturbative potential, so we need to have a UV potential. This phi to the fourth is what is able to fit the observation. And in the next slide, I'll say a little bit about UV completion.
Was this consistent with your motivation? You wanted a Gauss boson?
Yeah, so you very softly break that symmetry here with this potential. So you're a pseudo Goldstone boson. But
is lambda like absurdly small?
Yeah, yeah. So you're still having this protection on the mass.
If I turn off, I guess if I make F really big.
Yeah.
That's like making your epsilon really small.
Yes.
So that's going up on your picture here.
It's not actually, it's actually not so straightforward, the dependencies. The scaling is not, it's actually quite delicate.
I'm just wondering why it's not turning to where you would get the normal values of NS and R for the lambda phi to the fourth theory.
Because you're in the lambda phi to the fourth theory, when you match with the amplitude of the power spectrum, you have Hubble as you scale. Here now you have Hubble, the temperature, as well as the ratio of thermal friction over Hubble.
Yeah, but if I turn epsilon off.
If you turn epsilon off, well,
Right.
I'm not fully in the cold regime here yet. Like, because I still have, everything I'm showing here is in warm inflation, so temperature is larger than Hubble. I'm not smoothly transitioning into where temperature falls below Hubble.
This whole picture you fix F?
No, this is a range. I'm just giving roughly like what order of magnitude the range is. But this is yeah, this becomes fixed by the CMB observations. I can show you exactly like the range. But order of magnitude, we're between 10 to the 12 to 10 to the 14 GeV in terms of F. And the important point is that this F is this F that pops up here. So this is what we are probing with axion probes.
I'm a little confused because in the cold inflation plots, there's usually a line because they have basically one free parameter, like the lambda in your case, and they can trade that for n. But you have another free parameter here. So you have to fix
No. So F becomes fixed by the scale in the CMB.
But then how is lambda fixed? Like
lambda is not fixed. Lambda is varying. Lambda is what varies along this curve. So depending on what lambda is, for very small lambda, we get hotter. Or not hotter. For very small lambda, we go in the stronger regime of warm inflation. And this is why I'm saying that we still need to be quite flat. So as we make our potential more flat, our friction gets larger.
What's the H depends on?
Yeah, exactly.
Have you fixed the number of EFOL?
Yeah.
What's n star?
And so because you don't have reheating in this model, you can exactly calculate what the right n is.
Okay.
Yeah, so that's one point. You don't have this uncertainty in reheating in your e-faults because you're smoothly getting hot. So you can fix n. So that's why I'm saying that this is a point for each value, basically for any choice of your potential, there's a point where you live here. So what happens here, we directly transition into a universe filled with a quark gluon plasma, which is nice because that's our universe at some point in the past. So excuse me. I think here we're at 10 to the negative 14, and here we're at 10 to the negative 20. And now we can explain to how we can have basically live down here in this tensor to scale ratio plot for aquatic potential, and those potentials are already ruled out for cold inflation. Of course, there are other things you can do, but yeah, then you maybe have to modify gravity or something. So this is one way where you can have a simple chaotic power law inflation, and you're in agreement with all observables. And what I find very exciting about this is there is a smoking gun signature for warm inflation, and that lives in the non-Gaussianity imprints. There was a paper 10 years ago, and more recently a newer paper, and both of them have pointed out and identified that warm inflation leads to a unique bispectral shape that peaks differently than the cold inflationary models. So of course, the first step is to discover non-Gaussianities before you ask about specific bispectral shapes. But in principle, there's a smoking gun that distinguishes warm from cold. And of course, if you know that you're warm, you cannot say, okay, it was exactly this coupling. But since that seems to be the simplest one, it seems like a good candidate. Okay, I'm almost out of time, so I'm gonna go through this slowly. Now you may ask about dark matter and strong CP. I mentioned that we're accessible to axion probes, but of course a lot of axion probes assume that this is all of dark matter, our axion, the Haloscope's experiments. So what happens after inflation? So in this specific potential, the phi to the fourth, the inflaton redshifts away very quickly, either as radiation or it can go away even faster. And so its field, its amplitude will decrease, and eventually the QCD potential will form as we fall below the confinement scale. So then we have our regular cosine potential on top. And we checked, you end up being in the smallest, you roll to the lowest minimum of, basically you have a superposition of your phi to the fourth plus your cosines, you end up in the lowest minimum. But now what are the issues here? Because you decay away so fast, you don't expect this to be a dominant dark matter component. And this also does not solve CP. So in a way, you still have a tuning there to align those two minima with each other. So right out of the box, this mechanism does not give you a nice explanation for the strong CP problem. But the scale here, so in a way what we're predicting is a generic axion, one that is not dark matter or a very small component, but an axion that exists in nature that you can produce in light shining through wall type experiments or in astrophysical environments. And the scale that corresponds to the range I've showed you is 10 to the 10 to 10 to the 13. And there is much more to do. So on one hand, the power spectrum has not been computed basically for forms that are a little bit more unusual. Usually they just consider just the temperature dependence, but if you have a correction term, you go into regimes that have not been considered before, which is very interesting because to continue the curve I showed you into all possible regimes for QCD, you would want to know what the CMB observations are. Similarly, for not QCD, but other non-abelian theories, this chirality violation could be Yukawa scatterings or Dirac mass. And then you change the scaling here because you have additional temperature dependence. So you also enter different regimes that have not yet been explored phenomenologically. And then what I'm excited about thinking about, like I said, we didn't go into these regimes yet where this term becomes large because computations are insufficient so far. But I'm working right now on refining those predictions. And then the question is, if you go into those regimes, can this work with the quadratic potential? And of course, if it did work with the quadratic potential, then it would be much easier to UV complete because, for example, you could easily couple to another GG dual type group that gives you heavy instantons, where you get a cosine type potential that over some field range looks like an m squared. So that would be much easier to embed than the phi to the fourth, which I agree would probably be quite convoluted to get out of a full UV theory. And then what I'm excited about is looking at computing for all of these different regimes, and then also what are the state-of-the-art constraints on these non-Gaussianities. What I think is interesting about this is we're constraining with measurements from up top, we're constraining R, we're lowering R. And the non-Gaussiani constraints are strongest for the strongest regime of warm inflation, so it comes from below. It can rule you out from below. So in a way, you can probe this model or from both directions and maybe either narrow down a range or rule it out altogether, which, so I think it's great when we can rule out things too. So I'm going to conclude with maybe our universe has always been warm. Yeah, thank you.
So if you're using a lambda phi to the fourth, normally if you're doing lambda phi to the fourth inflation, you need to have phi of orders several times on phi. So where are you in that?
Yeah, so I didn't put the table in because tables are not so nice, but in terms of basically here, this was the range of lambdas that we looked at. And then as you go to smaller lambdas, you go towards the cold regime. So that then corresponds to larger field excursions. So that here you're at the 20-ish. But as you go basically very low on that plot, you end up at 5 M Planck in your field range. Was that your question?
It was. So I'm just trying to think your initial conditions. You've got your energy density. Let's just take the top line. If lambdas come to 10⁻20 or 21, then your energy density is 5 to the fourth factor of 1,000. So you're 10 to the minus 18 and 20 to the fourth. And so that's okay. So you're saying that's much larger than the T to the fourth, the energy density radiation. So you have your temperature is 10 to the 12 GeV. And somewhere on one of your last slides, you said that this keeps going on until phi is less than 1/10 of a GeV. I did something at the very end.
Well, yeah, at the very end, I was basically asking, what is the history of this field after inflation concludes? Basically.
Right, that's what I'm asking.
So eventually, there's the transition where radiation dominates is way before this 10 to the GeV.
Okay.
You transition into a radiation filled universe, but then your field kind of rolls to the bottom.
Okay. Normally, so again, if I turn off if I just consider the normal chaotic inflation lambda phi to the fourth, when I get somewhat around an M Planck, that's when my oscillations start.
Yeah, yeah. So it's similar. So and not quite around an M Planck, but for most of these, about 0.6 to 1 M Planck around there, you have the transition. Yeah.
Right. But so then you're oscillating.
Okay, so that's a good question. Are you oscillating? So not necessarily, because you still have this friction term that's overdamping you, right? Because here it's not Hubble. It's not a Hubble that dictates, and it's not steadily decreasing. You have your temperature, which is still steady state. So you can remain overdamped while you kind of settle into the minimum.
I'm still just concerned about eventually decay. Why doesn't decay just then force you down to the minimum?
But that's exactly what happens. Which is why I said you go to the minimum as radiation or faster. So the and faster considers all the processes that extract energy even more efficiently. The question I was trying to answer was just, does the QCD barriers form and do you get stuck before you're in the lowest minimum of the range over which the QCD potential forms? And there the answer is no, you get with very, very low, very efficiently and quickly, so that you get stuck in the lowest minimum.
By the way, this reminds me of people who use this for relaxing. as well,
Right.
where they use this decay to slow the field down and then save at the last minute.
Yeah, so very good. So David, my advisor was the relaxant. So,
Peter and David were on that first thing.
Why? It's like this is similar.
yeah, and in a way, this is something that I've been thinking about. Basically, what are the consequences for the relaxation mechanism? Because in relaxation, you also have a coupling of phi GG dual, and there are some regimes where this could matter, but for the relaxation, you also have inflation happening separately, which means you have a tunable scale in Hubble, and that can then make any effects from this irrelevant, even if you would expect it generically to be there.
So at the very beginning, you said upper mass of inflaton is protected because of U1 symmetry. And then I got convinced this phi is really not possible. Then you're introducing fourth term.
Well, it's a pseudo Goldstone boson.
Yeah, so then I think introducing fourth is not consistent either.
No, it is consistent because, okay, if you were perfect,
Why don't you have a T squared?
you do, but that's the thing. Even if you're not a perfect Goldstone boson, even if you're a pseudo Goldstone boson, you're still protected by that symmetry breaking parameter. So you've explicitly broken your symmetry with that coupling, but that breaking is small. You have this lambda parameter, which is small.
You can have a thermal mass.
So you do get a thermal mass, but what matters in that hierarchy is how large is that thermal mass in comparison to your friction. So you're correct I cannot say it's exactly 0, but the hierarchy and it is smaller than my dissipation. That remains true.
And when phi coupled to some non-abelian experiment, either the SU3 colored or SU3, how do you populate the standard model radiation? So phi inflaton decay to the hidden non-abelian gauge boson, and then this gauge bosons must transition, like must get transferred to the standard model radiation. How does that happen? Because this is non-abelian gauge theory, so there's no kinetic mixing.
So I started with a non-abelian theory, and then I said we're coupling to QCD. So
QCD is fine, but
what happens is we have the gluons, we're hot, so we're non-confined. All these gluons are scattering. If you have a hot gluon plasma, you have all the standard model particles part of your plasma.
No, I think he's asking if you had a
how
minimal.
about hidden non-abelian gauge theory?
Yeah. So
Oh,
like in some of your older works.
so
If it's abelian, then I understand.
Okay.
Kinetic, but non-abelian case we don't have kinetic. So how do you have a transition from the dark
I
radiation
see.
to the standard model radiation?
So there are many. You need to write down an additional coupling, but there are many ways in which you can do it.
What is that?
You could, for example, you could take your the inflaton itself and also couple it to standard model hypercharge, for example, because you also thermalize an inflaton in there.
So inflaton also decay to separate the standard model from that. So that's another.
That's one way. Like generically, if you do it for a non-abelian theory, eventually as the temperature drops, you could imagine that you eventually hit a confinement scale, and then you maybe form glue balls in that sector. But I would say I think if you're allowed to write down more couplings, there are very many channels in which you can couple additionally to the standard model. There's like it's not hard to, like if you're in a hidden non-abelian sector, there are many ways in which you can make dark matter or in which you can reheat. But it's quite unconstrained, I would say.
It's unconstrained, but I just want to be more complex. Maybe if you're saying like gravitational scaring, then I think that's one possibility.
Well, you can just write down any coupling, and then you can ask, is the rate of scattering larger than Hubble?
Yeah,
and then you can thermalize.
Then
sector.
those operators will become higher dimensional operators.
Well, no, you don't have to. So like if you want to take your pure SU into something, then you additionally have so not for this mechanism and not impacting this mechanism, you introduce some extremely light charge states like the up and the down equivalent. And after confinement, then you are making your hadronic whatever crap, and then you can couple the hadronic whatever crap to the standard model through all the tricks of the trade that you would normally couple, say, dark matter to the standard.
Yeah, or you can couple to the Higgs. You can also write down just a
That's
coupling to the Higgs
so that's
generically.
like one way that you can introduce like either you could even have massless quarks, but you could, anyways, you're introducing like a much lower scale, and then things are collapsing to that low scale after a confinement, say, it's still radiation, and then there's a bunch of machinery and pieces that you can tap on that people have.
Yeah, I believe the points of gauge very operator, I believe that, but they're very suppressed. They're associated, the induction rate is very suppressed. So I don't know how that could be compared to the Hubble scale. Maybe we need to wait long enough time to have comparable Hubble to.
Even if you have high dimensional operators, generically Hubble can be smaller in these models with warm inflation because the scale that connects you to the CMB can also be provided by the temperature. So generically, it's very easy to have interactions that are larger than Hubble.
So then compared to cold inflation, it sounds like here the potentials are just as tuned as maybe in cold inflation as well. So here it looks like the only thing you're getting different is just maybe different signals. It's not Gaussian. Is
Yeah.
that the story?
You get different signals, and I think the other thing is that if you have single field cold inflation, pi to the fourth doesn't work.
Yeah,
right?
yeah, but there are other models that work very nicely in cold inflation, right? Sterabins.
Yeah, but and then you have modified gravity.
Well, you know.
Yeah. No, I'm not saying.
There's sexy versions of it.
Okay, I'm not saying like this is. I'm just saying this is an alternative.
Yeah, no, I'm just trying to weigh up the two. So, but because I was just had the impression that maybe warm inflation you could avoid any tuning in the potential, but it sounds like you can't.
So I don't want to make a generic statement about that because in a way this fell a little bit out of comparing with the observables. So it may be possible that if you're able to explore all regimes phenomenologically, that is not the case for all of them. But for the one that I looked at here, I think that point is very much stands. That.
But you think that there might be more natural models for the inflationary potential with your setup? That's what you're suggesting.
Potentially, like.
Haven't people done warm inflation with the cosine potential? Natural warm inflation?
Yeah, and especially once you relax the standard model assumptions, then you have many more other knobs. Yeah, because this is great. But yeah, I'm here still exploring, like, because initially not all the observations were readily worked out. So I'm working on that now, basically looking at all the regimes and understanding if like an M squared, I think would be very nice. And I think there is also then maybe a nice story with dark matter there, because you could get relatively regular misalignment in that case. Just regular axion misalignment where, yeah, you have both. But I'm not sure right now whether it works.
Does your coupling to the gluons generate through one loop a quartic contribution?
No, I think that coupling just gives rise to the regular non-perturbative QCD. But
why not through loops? Can't I have a quartic? By the gluons, I have a gluon loop, and then I'll put three more if I can.
I mean, the 5 dual interaction is shift symmetric, right?
Yeah, so they don't appear in the
perturbatively,
equation.
It shouldn't give you any correction to the potential.
Yeah. That's exactly what I was going to say.
You told us the total.
All right, well, if you have more questions, Kim's here the rest of the day, and we'll go to Tea House tonight. So please let me know if you want to join, and let's thank Kim.
Thank you, and thanks for the engagement.